Yeah, hello everybody. So I'm glad to present about advancements in heat flow data, and in doing so, I represent somehow not only the group at GFZ who's leading this part as Project Innerspace, but I'm also glad to show results from SMU, University of Texas, and a large network of international scientists that contribute to the overall idea to provide an authenticated database on surface heat flow data. So when talking about heat flow data, not everyone will be familiar with that. It's clear that when you're measuring such kind of data, you rely on conductivity data, on temperature gradient data, and the type of heat flow you can determine in the subsurface then could reflect different geological conditions, can cover paleoclimate, and in particular, depending on the location, analyze different perturbing effects. Nevertheless, with covering these different dimensions, it can be relevant, and it is relevant for different branches of geoscience, so particularly the geodynamic modeling we're doing here, but also then geothermal resource assessments or general geoenergy resources, and it covers paleoclimate information. So it is in a lot of dimensions in the geoscience and an interesting parameter at the surface and interface between geosphere and atmosphere. So why do I present the whole thing here? I'm not only a postdoc at GFZ in Potsdam, I'm also a member of the International Heat Flow Commission, whose duty it is to collect heat flow data on a global scale. The Commission is doing this for more than 60 years now, but heat flow research is existing for more than 90 years. It is easy to see and understand that over such a long period of time, a lot of things changed in science and scientific methodologies and technology, not only in science, but also in general in society. So we had the process of digitization, data science coming up, and there's an obvious discrepancy between a compilation of data that is collected from literature over such a long time and let's say the increasing speed of change in terms of digitization and so on. So the question is here, what can we do with legacy data? How can we transform legacy data into something useful that can serve science today? And considers also the impact of past research on nowadays research questions. So with 90 years of research in such a database, it's the urgent question for the quality of what was collected over all the time appears, and this is actually what we are looking for, because there are quite common challenges when you're working with these kinds of compilations. Just some few are named here, like missing metadata, for example, an evolution of measurement methods and technologies. So a lot of things, this database went from hand to hand, from custodian to custodian, and went under a lot of changes and transformation in terms of the different requirements on digital data over the decades. For that reason, the International Heat Flow Commission, let's say, started a global assessment project 3 years ago, which was designed as a voluntary collaborative project. Currently, there are more than 100 scientists involved in this project. Up to 50 are currently actively working on the assessment of the global heat flow database, including the US data as well. So a lot of expertise from different institutes from 6 continents and a great network that is doing the assessment. And the major goals here is really to include more metadata. And as we have heard before, you need to know your data to understand the data, that you can use it in a meaningful way with reliable, let's say, uncertainties. So we are quality controlling the current database, and we are doing this and trying to do this with the understanding of the use cases of these data. So one intermediate goal in the past years was to define or to create a new global standard on heat flow data. We did this in 2 steps, and over the past 3.5 years, So with a lot of voluntary collaborative works, we created, let's say, globally community-driven accepted standards for the structure of heat flow data and for the quality of heat flow data in terms of guidelines. What is good measured heat flow? It was part of this process, or researchers in the US were also included in this process. From an example from the SMU, Maria Richards or Robert Harris. So the basic idea of this new standard or of this established standard is that we can give guidelines for what are the meaningful measures in heat flow, what are the important technologies here, what is needed to really come to a quality checked, authenticated database. And the goal with the standard is that we can create tailored data sets for different users that are quality controlled, so that the user is not relying on the primary publications anymore, that we can guarantee about what is included. There are two aspects. So the data structure change, the last definition were from 1957 from Jessup and colleagues. So we extended these fields and metadata from 18 to 62. The reason for that is that we wanted to have an extended documentation serving a so-called parent-child structure, and I will come to this in a minute, which is also based on a relational database system and not simple tables anymore. We have specified fields for borehole mine and marine data, and we defined also mandatory, recommended, and optional fields. And in particular, the mandatory fields serve then the basic idea of the quality scheme that can be applied later. What does parent and child elements means? Everyone working with databases knows basically in relational databases that you can have this kind of structure, master or slave, and now parent-child. Parent elements in this sense define the relevant heat flow data and the necessary metadata on a location level. And the child elements itself consist of the actual measurement information on heat flow conductivities, temperature data, and associated metadata in each respective interval. So that means you can store now several elements, several measurements for the same location in this database. And with that way, we are making it more flexible. We design a way that you can consider different kind of contributions from different authors, different kind of corrections applied for the same location. So there's a number of items or information stored on the parent level and the child element, or the child level. And it makes us much more flexible in terms that we can consider new methodological approaches later on and correct data when we have a better understanding for specific effects, perturbances, or so on. The structures mainly serve the idea also to apply an overarching quality scheme. So we defined a scheme. For all data here, we need 26 of the 62 fields for this quality scheme itself. And when you're in contact with heat flow data, then you need to know that even a technical, perfectly executed heat flow measurement can express unexpected geological environment conditions. So the basic idea of heat flow is that we can express the heat from the Earth interior, but depending on the geologic conditions, on the depth of your measurement, you are covering a lot of overruling environmental or borehole effects, and which gives you more information on that. And so we think that if we want to rate quality, we need to rate this in different steps. We can quantify numerical uncertainties, obviously, but we need also rate methodological reliability and overarching perturbing side effects that can occur at locations. This makes things a bit more complex. So we have all these elements for the database, some of them mandatory and thus relevant for the quality schemes. other just recommended as nevertheless important metadata. So how does this look like in details? So we compute on these three levels, three scores more or less. This is the so-called U score for the uncertainty quantification. Then the so-called M score for the technical reliability of the measurement, and so-called P-flags that reflect perturbing effects and the question whether those effects are corrected or not. All those things result in a combined quality score. And this combined quality score is then used for comparison between locations, between different measurements at the same locations, and can be then used for, let's say, a tailored selection of your data set itself. The U score itself, we calculate this by the COV and the error propagation values of the input data. And those COV data are then classified in different classes with the respective class ranges shown here. We use then the U1 to U4 as a classification, or the UX if data could not be documented because of missing documentation in the original publication. So the so-called M score for technical reliability really focuses on the technical quality or methodological soundness of the conductivity determination and the temperature gradient. So what we basically create is here a two-dimensional plot of two scores, the score for temperature T score and the score for the conductivity TC score. So this scores based on different aspects under these dimensions for which you can gain penalties or bonuses, and this then is yield into, let's say, a scoring that helps you to understand or to come up with a reliable estimation and a deterministic estimation of reliability for a specific location. And due to the different nature of borehole and marine or probe sending data, we have created two different kinds of schemes here. So finally, the third element are the so-called P-flags or perturbation flags. What does this mainly mean? So there are 7 perturbation effects we have defined in the following way that cover, let's say, sedimentation, erosion effects, topography or bathymetry effects, paleoclimate, short-term surface temperature variations, and then things like convection, fluid flow, and heat refractions. What does all these letters mean here? So we cover with these P-flags, we cover the ability or the information whether an effect is present or not present, and whether an effect is corrected or not significant. With this kind of information, we can, let's say, decide about the application of overruling corrections to data set, or the user can apply those corrections as these corrections and the specific information has not been recorded so far. So the combined quality score is then for the first time really a deterministic and transparent approach on all these 3 dimensions, and the release of 2024 of the global heat flow data set, which was published last week, by the way, is the first one where we applied this to the full global data set. This brings me to the current release of global data we have worked on in terms of the project inner space. So at the moment, we have a data set of around 91,000 data points, which is an increase of 25% since last year. It's dominated by continental data, clearly, and around 42,000 data points are currently quality checked. This is the result of the work within Project Inner Space in the last year. It required approximately 11 full-time scientist years to come to this point. This is not entirely funded by Project Inner Space, but to a large part. It doesn't mean that we have 11 scientists here. We are working with scientists, with students, with a lot of international scientists that are supporting as guests temporarily, or that are supporting remotely as well. what does it mean in terms of, for example, uncertainty quantification? Since we have worked on let's say, or reassessed half of the data on the global scale, we can, based on this assessment, judge on 40% on the data in terms of uncertainties. So this was not possible before in that way, but it also shows that this kind of analysis really depends on the quality of documentation and respective publications. If information and metadata are not documented, then it's hard to compile those data. Since our focus was really on the global data set, which did not include the US part so far, I would like to outline what this means for a particular region. I'm just showing this for Australia. In this case, so on the left side, you see basically the distribution of points we had last year. We had no clue on the uncertainty that was possible so far. So we reviewed around more than 90% of the data set. And now you can discriminate between the different uncertainty scores at this region, considering also what was not, where no uncertainties has been reported so far. The same is basically now possible for the methodological evaluation. So we can also judge on the different methodological classes here that describe the heat flow determinations itself. And the picture is a bit different compared to the uncertainties. And the third one, we also can now separate between the different perturbing effects, whether those effects are corrected for, whether they are not corrected but observed. And this for sedimentation topography here in red, the surface temperature variations in yellow, and the convection question, and with these circles also all that do not record any perturbing side effects. So with all three information, you really can go into more detailed analysis for these different dimensions. It allows you somehow then also an uncertainty mapping if you wish so in this sense. And if you use a joint information of uncertainty quantification and also the methodological reliability, then you can use it for some more in-depth analysis here of those joint groups. Helping you as model input, giving you constraints for the model calibration as well, which goes, I think, far beyond what was possible with surface heat flow data before. So what does it mean? This particular data set is now ready for refined geosystem analysis. You can use it for your as a tailored quality control data set. And it's quite nice. And time of the, or in the frame of Project Inner Space, there is roughly 40% of the data set of the world is open to review. The current release includes also around 20,000 data points from the US, but you will see in a slice that actually it's much more data available in the US. And I will show why. The global data set on which we are working is supposed to be finished in 2025. So let's come to the US. The data compilation I show here was compiled by the University of Texas. Convincing Mohamed Khaled. So credits to him. They compiled those data, they do not compile the Cornell, but they compiled the database for Project Inner Space based on the Cornell database. The SMU database is AASG. So they did a great job on that. All these databases has been converted into the IHFC structure, basically. And but what is missing so far is the essential information on conductivity, temperature, and side effects. So it was a structural merging mainly with some control. The add-on of the step 2, so the enrichment of metadata, is at the moment still missing. So basically, if you then go for uncertainty scoring based on what is included in this kind of compilation so far, this is there's a lot of things, a lot of way to go, because it's basically not assessed in the meaning of the word as we have done it for the other parts of the world, because this was not part of the Project Inner Space Agreement so far. Anyway, the question is, why is temperature not enough? I think we should look at this since energy transition and heating and cooling sector must take place in urban areas where you have a clear lack of borehole data. We really should go for, also in the US, for refined understanding of surface heat flow data, which requires really an assessment of original studies. So based on what was compiled in the project, we know that we need to assess around 300 sources for the 20K data and another 100 that are yet unclear for us for the 30K. So in terms of a QC data set, there's quite a way to go. So if we want to make US heat flow data quality assessed in terms of, let's say, the international standards, then this would be basically possible, but at the moment was beyond the scope of Project Inner Space. So with that, thank you very much also to University of Texas for the great compilation.